This is CFD Lab 1. Today we'll talk about ANSYS Workbench and ANSYS Fluent, and then we will perform a simulation of steady-state laminar flow in a pipe. These are the lesson outcomes. We will understand the basic layout of ANSYS Workbench and ANSYS Fluent. We will also look at the type of files that is used in an ANSYS Workbench or ANSYS Fluent project. We will also look at different ways to save ANSYS Fluent project and data files. This is very important since we will deal with, when we're running a project, we will deal with different timeline, people, many different cases. So the way you save a project will help you navigate projects better. And then we will look at the basic workflow of a CFD simulation, and then we will do that by performing a steady-state simulation of a laminar flow in a pipe, and we will extract meaningful data from the simulation result and present it in a proper manner. So this is the simulation these are the simulation objectives. We'll study the effects of flow velocity to the entrance length for laminar flow in a pipe. Also look at the effects of flow velocity to the velocity profile for laminar flow in a pipe, and we'll compare simulation result to an analytical result. This is our problem description. We will look at steady laminar water flow in a pipe, and since flow in a pipe is a mature topic, it has been studied by researchers for a long time. We know that for laminar flow, the Reynolds number will be below 2300. Okay, so we have for laminar flow, we will have we first have to consider the Reynolds number, and this can be done by this is calculated using this equation. Okay, so the Reynolds number is given by rho Vd over mu. Alright, and when the Reynolds number is below 2300, the flow is laminar, and when the Reynolds number is between 2300 and 4000, this is transitional flow. So the flow is transitioning between laminar and turbulent flow, and when the Reynolds number is over 4000, this is turbulent flow. And of course, these values are only used for pipe flow. Okay, internal pipe flow. For different types of flow, for example, flow in a square duct, or flow between two parallel plates, the numbers will be different. But these numbers can be used to describe flow in a pipe. So in our case, we will look at cases where the Reynolds number of the flow is below 2300. So we will have the flow inlet, and then this pipe has an internal diameter of d, and then we'll have the entrance region, and the entrance length for laminar pipe flow can be calculated using this equation. And then after the entrance region, the flow will be fully developed, and right here, since this is a steady flow and the flow is fully developed, the velocity profile does not change with flow in this direction, in the x direction. Okay, if you assume that this is the x direction, and an analytical solution of the velocity profile for fully developed flow is given by this equation. Okay, so we will perform a simulation for this pipe, and we'll compare the result of the simulation to this analytical solution and see if how different it is they are. So let's start with this. Okay, so the pipe has a length of 10 meters and the internal diameter is 10 millimeters or 0.01 meter, and the material is water, and the velocity V in is uniform at the entrance. So this is what we will these are the parameters that we will use for our simulation. So first we will start with the ANSYS workbench. Okay, when you open ANSYS workbench, this is what it looks like. So you have in the middle the project schematic, and on your left you have many different analysis systems. Most of it is not related to fluid flow. Okay, you have different kind of analysis system that you have under the ANSYS workbench set of applications. And on the right side you have properties for your project schematic. So what we do first is we right click and we can create a new analysis system. When you create a new analysis system, the workbench will give you a workflow that you can just follow. So for example, we will use fluid flow fluent with fluent meshing. When we click here, we'll have this box here that represents our analysis system. What we do next is we will just follow this flow from top to bottom. So what we will do is we will just follow the flow of this workflow from number 1 to number 6. Okay, and then this will complete your project, your simulation, and each part will be done in different applications. For example, for geometry, okay, let's take a look at geometry. So first, this is what we'll do. Number 2, geometry. This is where we'll prepare our geometry, and this can be done by double clicking it or right clicking it, or if you just click once, you'll have your properties on the right side. So in our case, we will perform a 3D simulation, so we will set here as 3D, and we don't need to change the others, but you can take a look at the properties that you can see here. Okay, you can change what you need to change, but in this simulation we do not need to change anything. And if yours are set as 2D, you can choose 3D. And when you right click, you have new discovery geometry, new space claim geometry, and new design modular geometry. These three are different types of CAD software, CAD application. So we will use space claim. So just click on new space claim geometry, and once you do this, ANSYS will open a new application, space claim geometry. This is space claim. So this is where we will create our geometry. This is very similar to any other CAD software that you might have used, for example SolidWorks or Fusion 360. So you have your sketch tools here, and you have your design tools, display assembly, and all the tools that you should be familiar with, especially because you have already learned about CAD and you have already used CAD software. So this is where we will create our geometry. So let's draw our geometry here. So you have your X, Y, and Z axis. Let's draw a circle on this plane. the center of the circle will be the origin of this axis, and according to our geometry right here, the inner diameter of our pipe is 10 millimeters or 0.01 meters. So that's what we'll set here. So this is the units in millimeters, so we set this is 10 millimeters. All right, so now we have our pipe circumference, the circle, and we can look at this from the top here. All right, and if you click the middle your middle mouse button, you can pan this the view, this viewport. Okay, if you click control, if you click control and middle mouse button, you can move it around. This is only the middle mouse button, and this is control and middle mouse button. So next we will on this top menu we will go to pull. Okay, we will select this face and pull it out, extrude this, so it will become a pipe. So click here, pull, and we can pull this up, and the length of the pipe is 10 meters long. It's 10 meters, so 10 meters is 10,000 millimeters. So that's what we will write here, 10,000 millimeters. Press enter, and you will have the geometry of your pipe. Okay, so this is a very long thin pipe. Now the geometry is done, but we cannot stop here. One thing that you need to do before we move on to meshing and then setup of our problem, we need to name the boundaries, so it is easier for us to set the boundary condition in ANSYS Fluent. So if you look at our problem description right here, okay, I will so we have a pipe, we have inlet, and we have outlet. I will draw this. Okay, this is what it looks like. We have our inlet right here, and we have our outlet, and then we have pipe wall. Okay, so this is actually, so if we have a pipe that looks like this, a pipe will have a pipe wall. Okay, and the pipe, it will look like this. This is a 3D pipe. Right, so a pipe will have a pipe wall, so the pipe wall will have some thickness. For example, this is 1 millimeter thickness. This is just an example, it can be any thickness, right? And then pipe will have pipe length L, and this for our case is 10 meters long. So this part, the part that we perform simulation, will be the part where of fluid in the pipe itself. So what we will model in our CAD software is this part, is the fluid part. Okay, not the wall, not the thickness of the wall. We do not need to draw the thickness of the wall. So what we will extract from this pipe is only the fluid region. Okay, only the fluid region. So basically what we have here is only the fluid region. This is the fluid region. That is why the diameter that we use here is the inner diameter, which represents the diameter of the fluid tube. Okay, fluid tube. So this is what, If we extract this out, this is what it looks like. It looks like the pipe, but where the diameter of the fluid is the inner diameter of the pipe itself. So this is what we will simulate. Okay, and flow will come in from one side. So the flow will come in from this side. This is what we call the inlet. This is where we will set our boundary condition, our inlet boundary condition, and flow will come out from this side. So this side, this surface here will be our outlet. This surface is our inlet, the other surface will be our outlet. Okay, because it is connected to the outlet of the pipe, and the surface that is here, the other surface here, they are all it is a surface that is touching the wall, is connected to the wall, it's next to the wall. Alright, so this surface is wall, we call it wall. Okay, what happens is the velocity will be 0 due to the no slip boundary condition. Okay, so these are the 3 boundary conditions that we need to define or name in space claim. So that is what we will do now. So okay, first thing, let's name this. We look here on the left, let's name this fluid. So right click or double click maybe, or right click, rename and name this fluid. It's not really that important, but ANSYS Fluent will recognize these names, and they will change the settings according to the name. So if we can change the name now, it will be much more helpful once we set this problem up in ANSYS Fluent. And then when we go to groups, okay, this tab here, we go to groups. Okay, so if we look at the here, this is the surface that where we will set this as the inlet, right? So we click on the surface, we select the surface or this face, okay, and we click here, create NS. NS is name selection. So we click here, and then we will have this group 1, and this is where we change the name to our boundary condition. So we name this as inlet. So now we have already set the name of this face or surface as inlet. So if you click here, this face will be selected. So we do the same for the outlet. So if you go to the outlet, to the other end, we select this face, okay, and then we click create NS, or create name selection, and we name this outlet. Enter. Okay, so when we click outlet, this will be selected. And then final one, we select the face that surrounds this tube, this fluid, and we create name selection. We name this wall. Enter. Now we have define our geometry. This is the fluid in a pipe. Okay, this is our geometry. So once we are done, we're done with this. We can save this. Okay, if we click save as, we will save this as can save this as a space claim file, sc.doc. Okay, so this is a specific type of CAD file for space claim geometry. Okay, we can save this, for example, height. You can save this, but when you save this, we will not save it as we still have not saved the project. Alright, so we need to click file and click save project. So when we save this project, we will we can save this now. Okay, Laminar. Let's say we save this project as Laminar pipe flow. Okay, so the type of the file that we save when we save a workbench project is WBPJ. So WBPJ is the workbench project. If you click save, so it will save not only this geometry, not only the space claim file, it will also save the entire project from the ANSYS workbench. So we are done here. We can just close space claim, and you can see next to geometry we have the tick. It means that we have already performed this part. We have already completed the creation of this geometry. Right, and then since we have already saved the file, if we go to the folder where we saved the project, we can see that we have this pipe. This is the geometry file for space claim .scdoc, and then we have our workbench file, WBPJ file, and also we have these two folders. These are this folder, the first folder, Laminar pipe flow files, will be where the simulation files will be saved. We will look at this once we run a simulation. The files will be saved here, and we need to understand the structure of this files and folders, because it will save using names that you need to be familiar with. Once you run the project, you will run many cases, and you also run many iterations. So the number of files will grow very quick, and you need to be able to identify the files that you're working on. But we'll look at that once we get to that point.